The last topic we're going to look at is magnetic potentials. The basic idea here is that we want a useful relationship for our magnetic fields the same way that we had for our electrostatic fields. And so recall for our electrostatic fields, we were able to say that our electric field intensity is negative the gradient of our electric potential V. And so that turned out to be useful in a lot of different situations, particularly when we were looking at solving using our boundary value conditions. So our potential was very important there. So it turns out, of course, we can define a magnetic potential, otherwise we wouldn't be talking about it. And we have two different types of magnetic potentials depending on the characteristics of the problem. We'll see in some cases we can't have one of the two types, and depending on what we're looking for. So we can have a scalar magnetic potential. So our scalar magnetic potential we're going to call V sub m. And so of course V for potential and m to indicate it's a magnetic and not electric. We can also have a vector magnetic potential. And so our vector magnetic potential we're typically going to represent with the vector A. So before we talk about the definitions of these two vectors in more detail, let's recall a couple important properties from our vector calculus. So this was chapter 3 in the textbook. So the first one is that the curl of the gradient of some scalar, so the curl of the gradient of some scalar, and I'm going to call it V, is equal to 0. We also had that the divergence of the curl of some vector, so the divergence of the curl of, let's call it A, is equal to 0. So let's sort of keep these two relationships in mind as we're going through and defining our magnetic potential equations. Okay, so let's start with our scalar magnetic potential V sub m. So we're going to define this magnetic scalar potential as H is equal to negative gradient of, let's see if I can draw that a little bit better, negative gradient of V sub m. So very similar to what we saw with our electric potential up here. However, we need to add one condition to this. We need to say that this is only true if our J is equal to 0. So if we have 0 current density. So why is that exactly? And so before we move on, let me go ahead and say this is our Vm is of course our magnetic scalar potential. And so an interesting thing is that our units for this potential are amps. So kind of confusing, we're talking about a V and it's in units of amps. But it makes sense if we think about our H because of course it's related to our current flow. Okay, so why do we have this condition that our current density has to be 0? Well, let's think back to Ampere's law, or third Maxwell's equation. In the differential form, we said that our current density is equal to the curl of H. So now let's substitute this equation up here. So we can say, because we have defined our H as being negative gradient of Vm, so let's just go ahead and substitute that. And now what we see is we have this condition that we talked about up here. So we have the curl of the gradient of some scalar value, so we know that this has to be equal to 0. So what that's saying then is that our J is equal to 0. So we know that this relationship then can only be true, our H equals to negative gradient of Vm, if our J is equal to 0. So that's where that stipulation comes from. So what that's saying is that our Vm is only defined when we have 0 current density. So only defined in a region with J equals to 0. Okay, and so as I kind of hinted at earlier, this magnetic potential is also going to satisfy our Laplace's equation just like our electric potential. So that means we could use it in similar boundary value problems like we saw in a previous unit. Okay, so now let's move on to our vector potential A. So we know from our fourth Maxwell's equation that the divergence of B is equal to 0. And we also know from equation 3, we know from from chapter 3 rather, we're going to keep this guy in mind here. We can define our magnetic potential such that B is equal to the curl of A. And so again, sort of looking back at this equation, we know that the divergence of the curl is equal to 0. And so of course we know from Maxwell's fourth equation, so let's just write that here. So this is Maxwell's fourth equation. We know that that divergence of B has to be equal to 0. So if that always needs to be 0, let's just define B as the curl of some vector. And that vector we're going to call our magnetic vector potential. So magnetic vector potential A, which is going to be is going to have units of Webers per meter. So we're not going to look at the alternate definitions of our magnetic potential vector A, but we can also define A in terms of current. So can define A directly from currents. And so those equations end up looking very similar to what we saw when we were dealing with infinite current filaments, or rather not infinite current filaments, but a line current, a surface current, a volume current, or even thinking back to our electrostatics when we were dealing with a line charge, a surface charge, or volume charge. We had some integral form, we had to figure out a dl, we had to figure out a direction, so those equations look very similar to that. And so those can be found on page 320 and 321 in the textbook if you want to see that a little bit more. We're not going to get far enough to use those forms, is why I don't want to show them here, but they're particularly useful when dealing with antenna problems. Again, unfortunately, another interesting topic we won't have time to get to. I do want to note one other important equation where we can use this magnetic vector potential though, and to do that, let's start with the definition of our magnetic flux. So we said the magnetic flux is the integral over the surface of B dot ds. Well, we know then that we can substitute this expression for B, so we can say this is equal to the integral over the surface of the curl of A dot ds. And now this, again, we can use something from our vector calculus unit. So we can say, well, if we have the integral over the surface of some curl of a vector, we can convert that to a line integral around some closed path. And so that's going to be the line integral of A dot dl. And so that is using Stokes theorem. And so, of course, relating our line and our surface, so this line is the line that encloses our surface. So for instance, if we were talking about some arbitrary surface S, then this would be our path L that encloses the surface. And of course, dl is just going to be some differential length along that path. So what that gives us then is an alternate way to define our magnetic flux. So as we see here, we can now define our magnetic flux in two ways. So the first equation we already saw before, but now we have this new equation, which can be the closed integral of A dot dl. So depending on what information we have available, you know, it might be easier to do the surface integral, or it might be easier to do this line integral. And so we'll talk about that a little bit more in the example we're going to look at in the next video.